Hey everyone, welcome to another episode of Eigenbros. Make sure to like, comment, share, subscribe, follow us on our social media, right? You know, Terrence can fill in on this.
Instagram Eigenbros.
Yes.
Eigenbros on Twitter, Eigenbros2 on TikTok.
Yeah.
And then patrons, guys, we love you.
Thank you.
We actually do love you.
We do.
In many ways. And guys, if you want to join the Patreon, it's patreon.com/Eigenbros. Me and Juan, we do a 30-minute audio podcast there at least every week, and we have the Discord channel.
Yeah.
If you guys want to check that out, reach out to me and Juan. We talk about all kinds of random stuff there.
Yeah, we do.
So, guys, check that out. Support your boys, too, if you can. $1. Feed an Eigenbro.
Yes, feed us, please. And then last but not least, I guess, getting into the show, right?
Indeed.
Let's talk about
kind of the most important part.
Yeah, we're doing this week. We're doing qubit stuff.
Mm-hmm.
At least learning about qubits and just what the hell are qubits. If you're like one of these people, they're just like, I always hear about qubits. What are they?
We always hear the same goddamn explanations, though.
We do.
0 and 1 stayed at the same time. Blah blah blah.
But sometimes,
boring.
But sometimes it's a little bit unsatisfactory, right?
Yeah.
You're like, I want to know more. I want, hopefully this podcast we can discover together.
Yeah.
What a qubit is.
Unfortunately, I wish I could give more insight.
Uh-huh.
I feel like I'm pretty good at intuition.
Yeah, I feel like you know this stuff already, which is probably why you're just like.
But no, the shitty thing is with quantum mechanics,
yeah,
you can't really even invoke intuition. Because when I start invoking intuition, I'm giving people the wrong image about some other aspect.
Oh, I see.
Because it just doesn't follow classical intuition. So when I'm saying something about the qubit in an intuitive way, I'm fucking you up on something else that's a different concept related to qubits.
Mm-hmm.
So unfortunately, guys, I can't really give you a great explanation on qubits. All I can say is that it's got some mixture of states between 0 and 1, and it could be modeled on something called a block sphere. So it's like you can model in 2D or 3D space. Whatever the hell that means, it's some abstract thing. But unfortunately that's quantum. It's mathematics, and the only way you can really understand it is if you get into math. So if you're a diehard physics enthusiast like I was, before I started physics, and I loved all this physics stuff, talking about quantum and all this stuff. Unfortunately, guys, if you want to really know more and really know the deepness of the universe, especially in terms of quantum, you got to learn math. So you might as well just learn physics.
Pony it up. Actually, you don't even need to learn physics. Quantum mechanics is its own beast, truthfully.
It is.
So,
it's highly unsatisfying if you want intuition.
Yeah.
Intuition and quantum just are like, it's like, what is it? Peanut butter and orange juice.
No. Toothpaste and orange juice.
There you go. Thank you. Yeah. I knew it was something like that.
I was like,
but peanut butter and orange juice probably doesn't taste good either, does it?
Is
it okay? It might be
for a period in my life, I will say I had every day after school I would be looking forward to peanut butter and jelly sandwich, but
with milk though, I would imagine.
No, with orange juice.
Really?
Yeah.
Okay, so retract my analogy.
Yeah. This is why I was kind of shocked that you even said that, because I was like, wait a minute, it's actually not that. It's not as bad as it sounds.
Right.
Well, the thing is, the sandwich.
I offended your childhood
you spoke
memory.
too soon. No, because back. Okay, I invite you all to do this, but take like 2 waffles and sandwich peanut butter on one side, jelly on one side.
Yeah,
and that's your that's the peanut butter jelly sandwich, but then like have a nice glass of orange juice, not from concentrate, by the way.
This is a fat boy creation, Juan.
I was a fat boy. This was when I was going through puberty and I was very hormonal, and so I was eating weird food combinations, and this was one of them. So
basically, a teenage boy is like a pregnant woman.
Yeah. Truthfully, yeah. Very hormonal, angry at the world, just hungry all the time, wanting to sleep. But yeah, please try it out and let me know try it out, and then let me know if you liked it in the comments.
That's our homework for today.
Yeah. But in all seriousness, like quantum mechanics is a topic. If you're a first time listener, is one of these like topics that you can really just learn on your own, like on its own. Sorry.
Yeah, on its own. It's tough to learn on your own, especially if you're not
Yes.
familiar with anything in physics.
Yeah, but you don't need to have any preconceptions of physics because it's this really own field that you have to learn. You can get by with linear algebra, which is literally just algebra, like more abstract algebra. But all you really need is like to be familiar with a system of equations and linear algebra. Like linear algebra is like how do you manipulate these?
But you also got
to
to know calculus,
I think
differential equations.
that's if you want to learn Schrodinger's stuff.
But that's all quantum.
Yeah, I think that's an aspect. But I'm saying you can get by with linear algebra if you wanted to. You know what I mean?
I disagree.
Like Heisenberg
you
model.
won't even get like the wave functions without knowing calculus, right?
Yeah, I mean that's an aspect of it, but I'm saying you don't. You can survive off like which model you can survive off most of from my perspective.
Yeah.
Is using matrix mechanics. Is using just purely Dirac notation. You can survive off of that, especially in the language of quantum computing. Because I mean I haven't really seen somebody use a Schrodinger equation in quantum computing for the most part.
Really?
I mean, I guess
Well,
when
how
you
do you
get to
the
Josephson
Hamiltonians
junction
and stuff? You got to.
I mean, yeah, but
You got to get Hamiltonians and wave functions.
yeah, but if you have the wave functions, you can build it into Dirac states. You know what I mean? You can symbolize them as like.
Yeah, but how do you even
bracket.
solve for the wave functions? Is what I'm saying.
I mean, I see. If you're saying fundamentally at a deeper level,
Well, not it just. Well, I don't know. Maybe
Yeah.
you can get away with linear algebra if you're talking about like using Python to do.
yeah. If
quantum
you're doing
stuff
like,
or
imagine
something.
if you're doing like,
Okay, yeah.
yeah. You get what
So I
I'm
guess you're saying like just like if you want to just jump into like working with quantum computers,
saying? Right.
not necessarily like solving the wave functions or stuff. You just want to like mess with a quantum computer and make a quantum gates and stuff.
right. Let's say.
Okay,
you're
you're
an
right.
engineer.
You're right.
Yeah,
You're
yeah.
right. I think you're correct. You don't need calculus and all that. But if you're trying to do it from a physics side, and trying to like come up with wave functions or something, or just solve for wave functions, then you're going to need calculus. So
100%.
I guess it's like the two things you would need are calculus and linear algebra. But anyway, I'm sure a bunch of our audience already knows that.
Well, I mean, if you're an engineer, yeah. I mean, if you're an engineer, the linear algebra is going to be super useful. If you're a computer scientist, you probably already know linear algebra. So
Yeah, but they can pony up. They can what do you call it? Not pony up, but
survive.
solidify their knowledge. There's a better way of saying that, but anyway,
Sure.
they can
Navigate it.
no, they can always refresh their linear algebra skills because linear algebra goes deep. There's a bunch of concepts that you can know from linear algebra. Every time when I was during the summer, I was tutoring linear algebra. I'm like, damn, I really don't know linear algebra. Like, there's so much other crap that you can know, like just the relationships and the interesting techniques and things that you can know with linear algebra. I mean, it goes deep.
Yeah, especially for quantum mechanics. I mean, whenever you get to these qubit systems, you can get into. Usually, it's like a 2-qubit system where it's like the simplest.
Yeah, that's probably
Right.
the simplest I think that you can have with a quantum computer
Yeah.
to do any meaningful calculation.
Yeah, which would give you what, a 4x4 matrix, right?
I think you're right,
Yeah.
but I don't know if you can represent it other ways. Maybe,
Yeah.
I'm not sure.
But in that case, yeah, you would have to be familiar with the concept of polymatrices, and matrices that essentially matrix mechanics, which is just a fancy way of like doing mathematical operations on representations of your system in linear algebra.
Right.
Right.
And I remember your comment actually in one of those videos where you're talking about how when algebra students are doing matrices and when you're in high school,
Oh, yeah.
and you're like, what the fuck is the use to this? And you're like, you're basically doing quantum mechanics.
Yeah.
Like, that would have been cool as hell to know when I was a kid. Like,
Oh, yeah.
just knowing that is the math of quantum mechanics. So for people who are like laymen who watch us, like the matrix shit that you used to do in high school,
System of equations,
yeah,
yeah.
in algebra 2 was it or something?
Yeah.
That is literally the mathematics for quantum mechanics.
That's what we do. Like,
Yeah.
Yeah.
So it actually is useful if you can believe that.
It is. But they never tell you that. But it is super useful, and
Yeah.
it's the foundation for doing quantum mechanics. But, and I think if you want a little bit of history context, Heisenberg was the one. So Schrodinger's equation came first, and it wasn't until Heisenberg came and did his whole formalism of matrix mechanics that it gave you a wider breadth of application, because Heisenberg's equation was more like a theoretical model fitting. And
You mean the H.
I mean, Schrodinger's equation. I'm
Okay,
sorry. I'm so
okay.
sorry. My mind's.
Yeah, I was thinking of the inequality. I was like, okay.
I'm sorry. I meant Schrodinger's equation.
Yeah.
It was more of a theoretical model fitting thing that was kind of discovered early on, and then
Yeah, like he just derived it based on what he wanted out of the equation.
Yeah.
And I think to this day, even there is no actual derivation of the Schrodinger equation. There's like a pseudo derivation, but you can't get it from like
First
anything
principles.
else. You can get it from first principles, but you're kind of like forcing it to be.
Mm-hmm.
It's like some things are unqualified, I think.
Mm-hmm.
Like it's like you just know you want something that's a first order differential in time
Mm-hmm.
that has a second differential in space or something.
Yeah.
But there's no reason for that really. It's like there's no actual derivation.
Yeah.
Which is interesting.
Yeah. I mean, I think, well, I don't want to be disingenuous because when we talk about some of the qubit systems, specifically the best one, which is probably you've heard of or maybe you're not, maybe you haven't because that's why you're listening to this. So
Yeah.
the most famous qubit system, or the most useful one that we have right now, or the best, is the superconducting qubit, right?
Some would say, and others
Yeah.
would not, because
Others would not?
the one that's most widely used in universities is trapped ions.
I think because they're cheaper.
Well, and I think because universities are more adept at working with trapped ions as well.
Mm-hmm.
But the scalability of superconducting qubits in industry, goes really well.
Yeah.
So industry tends to use the superconducting qubits. I believe that it's like IBM and IonQ and who else? Does Rigetti use it? Do you know?
There's a huge list, and we'll go ahead
Yeah.
and put it up on the YouTube page here.
Google, I think, uses it as well.
Yep.
There's Sycamore.
Yep.
A bunch of the big people use.
I think there's like
superconducting.
Cold Quanta and Boulder. I think they also use superconducting qubits. There's three essentially. There's molecular ones.
It's types of qubits you're saying?
Yeah.
There's
like
more than three.
Well, the three
They're
most
just
famous
major,
ones.
maybe what you're saying. Okay.
The three major ones, the three top ones that I've seen, are the molecular ones, which are kind of the least used. And then there's, although they still have long coherence times, and we'll explain what that is in a little bit. And then I think the second one is the trapped ions. I think
I have on my Twitter.
Yeah, they have different names, but the trapped ions are, from what I've seen, there's like basically nitrogen vacancies or something in diamonds that they create.
Maybe, but I know there's also a diamond vacancy.
Yeah, that's what I'm talking about.
One, so I don't know if that counts because
You know if
trapped
that counts
ions.
as the trapped ion system.
I don't know if it does because I think trapped ions are just literally just trapped in space by lasers.
Oh, I see. Okay.
But maybe there's other configurations. I don't know.
Well, so let me make this distinction here. So there are qubits that are formulated using defects, and like, have you heard of this one? Qubits using
I think so.
Yeah, so
maybe we should title this one like two physicists who don't know shit about quantum computing talk about different types of quantum qubits.
we learn we're learning with you folks now.
In this episode I will qualify as is less prepared than normal, so we're going to hopefully let the videos that we play and things like that do more of the heavy lifting.
Yeah. But we definitely, look,
we're just talking.
I brought some notes.
Hopefully we won't say any wrong shit. This
is why I brought notes, because I thought, okay, here I'm going to teach you some here, Terrence.
Okay.
So here we go.
Learn me something.
So qubits, I'm going to post up this article, but that I received from the Department of Energy website. But there are qubits using defects, and defects are spaces where atoms are missing, are missing in a material structure. They change how electrons move in the material, and in certain quantum materials, they trap electrons, allowing researchers to access and control their spins. And unlike superconducting qubits, these defect qubits don't need to be at, or don't always need to be at, ultra low temperatures, because to reach superconductivity traditionally with most superconductors nowadays, you need to go to really, really low temperatures. So the defect qubits have the potential to have long coherence times and have scalability.
Okay.
And they do this with, like you're saying, the diamond
Vacancy.
The diamond vacancy one,
Uh-huh.
because diamonds are usually valued for their lack of imperfections, but there are these defects where adding a nitrogen atom to a place where there would normally be like a carbon atom, you would create a nitrogen vacancy, and physicists use this vacancy to basically a couple nanometers long, really, to create defect patterns, and then the spacing helps increase the qubit's coherence time and makes it easier to entangle your electrons or whatever. So you can put more electrons into this vacancy, or excite electrons into this vacancy, in this nitrogen vacancy, and create a quantum computer.
Is it that easy?
From A to B, baby. No, I'm just kidding. Magic, nitrogen vacancy,
Quantum computer.
plus magic,
Right.
Equals quantum computer.
It's like that old meme, question mark profit?
Yeah. No, but they've done the same for cheaper materials like aluminum nitride and silicon carbide. And the silicon carbide one is actually more promising because semiconductor manufacturers work with silicon all the time, and they have this down to a science, like creating defects and stuff. So that seems to be the most promising one, but I think the limitation there is something that we've been referring to called coherence time, right?
Big one.
Yeah.
So coherence time, just a little quick explanation for the audience again, is basically how long your superposition state lasts for qubits. So then you might be asking, okay, now you just introduce another word, superposition. For those who are not familiar, superposition is that state that allows the quantum computer to be quantum, where it's in a 0 and 1 state at the same time. Which basically is just saying, like, yeah, there's like this weird combination state you can have with a 0 and a 1 state instead of the classical bit, which can be either 0 or 1 only. Of course, when you measure a quantum qubit or whatever happens, if the quantum bit interacts with anything, you always see it as either a 0 or 1. But the magic lies in that kind of behind the veil where you don't know what it is in that 0 and 1 state.
You're not interacting with the system.
Yeah, it's and with that, and there's some weird shit that goes on behind the door where, because it's in that mixed state, it has a different probability distribution than a classical bit would have. So classical bit cannot do quantum computations because it doesn't have that same weird probability distribution that you can have when you have that superposition state. If you don't understand what that means, fine, it's okay. It's not that serious. It's just remember that superposition is what makes things quantum, and entanglement as well, which is related. And then classical does not have that property. That's how they are distinguished.
Yeah. And superposition is a purely quantum thing. Like, this is why I was saying you really don't need to know any other, you don't need to have any conception of physics. That's its own it's its own principle of quantum mechanics.
And I think that is an axiom of quantum mechanics, is it not?
Yeah, I mean, the states are a linear combination. That's
right. Yeah, so I think superposition is a quantum axiom.
And so the thing with, it's kind of hard to get an intuitive picture because physicists also get caught up in a lot of the math, and then the math formalism can be elucidating. It can sort of point you in the right direction, but you don't want to get caught up in trying to get a physical picture of this because you will get lost. It's a lot of math.
Because our brains are not made for it.
Yeah.
I think trying to get a physical picture of quantum mechanics is a futile effort because we can't think like quantum creatures. We are classical. Right. We are a squared in flatland.
Right.
We just cannot think like.
But I mean, like, creature. Well, there's a discussion to have here because there are physicists that say, well, the wave function isn't real until you square it, but because you have like these imaginary terms, which is like silly terminology because it doesn't really mean that it's imaginary. This is a mathematical construct.
Well, I think they know that. It's just complex terms. But the thing is, we don't measure anything complex in real life. So what the hell is a complex number
but the thing is, like, for me, I would argue that, when you look at the s equals 0 orbital of like the helium atom, where it's like just as purely spherical, you see that when you take data. Like you see the SPDF orbitals, right?
But that's nothing to do with imaginary numbers.
Well, I'm thinking about the wave functions.
Yeah, but just like you said, it's when it's squared.
Yeah.
You see the real squared version.
Mm-hmm.
But that's
I see what you mean.
That's the measurable state. That's why it has to be squared, because it gets rid of all that imaginary number crap and it gives you a real number or real state.
Okay.
We don't ever measure not real states.
Yeah, but my argument is that what you're seeing is not the wave function.
Right. The wave function is just this weird, cool thing we discovered from quantum mechanics that we would never know about if we didn't have the math.
But this is the thing about the physicists, though, like, or when we have discussions about this, to me, it's like, the wave function to me is like, you're piercing the veil in some way. Like, you're not.
That's almost why physics is magic. Because you're literally seeing things that you would not see, that you can't determine from reality unless you just have all those connections with the mathematics.
Right.
The mathematics is like this magical thing that you're bestowed that you can't really even there's no way to know that in reality. Like, the only way you would know that is just because it follows the math. You're just scratching your head like, what the hell is going on? But as soon as you figure out the math and realize that it aligns perfectly to what you're seeing, that's why you know the math is right.
Yeah.
So it's like you're saying, we are seeing behind the veil. Yeah. That's why physics is this weird thing. It's almost like you get to see Narnia, you know.
Well, I want to give
some weird way.
Well, in some ways, I do want to give a good illustration to kind of give you an analog of what might be happening here. Is if you ever see like at least with wave functions, if you've played with a jump rope. Yeah. And you're standing with somebody on the other end and you start shaking it vigorously, you'll start getting like, we say a superposition of waves. Right. So you start seeing like standing waves and nodes and stuff. And we use these concepts in quantum mechanics because they're very analogous like to the math, right? Yeah. So you see like you basically, if you've ever done it with a friend, sometimes you'll see that there's one bump or whatever, and then sometimes if you shake it hard enough, if you use more energy, you create two bumps, and you can think about
nodes, as we call them.
Nodes,
or maybe I forget if it's node or anti-node. I always forget.
Well, one anti-node because if you have two nodes, but
okay. I'm saying, am I using that right, or is the bump the anti-node?
No, I think the bump is the node.
I don't know.
Okay, well,
I'm gonna bow out of that one and just say maybe, I don't know, whatever it is. The bump is whatever.
So, but the idea is that if you've ever seen one of these, if you've ever played with a jump rope, that's kind of a good way to think of the wave function. What people mean by like a superposition of states, because with the jump rope analogy, you can't say, is the jump rope in a like which. How would you say, which state is the rope in at any point in time? Okay. You know what I mean?
No, I lost you a little bit.
At which, like if I asked you if I was doing that with the jump rope and oscillating it back and forth, at which point could you tell me, like, in which state is the rope in? In which nodes, like in which, do you know what I mean? Like which state is the rope in? Is it like, does it have both nodes, or is it just the left one or the right one? If there's two nodes, there's two bumps.
I don't really understand.
You don't follow
the question? Okay. No.
My question is, I'm trying to create an analog to superposition, so people.
That's the problem. I don't think you can.
I think
because the quantum one, the whole wave function is just telling you a probability wave, right? So we always measure.
It is, but
yeah, that's square. I'm sorry. Yeah. So the thing is, when we measure that, we always know. We know that the wave function itself is just showing you all the possible places, all the possible probabilities of where the particle could be.
Let's talk about purely electrons here. So
so where the electron could be, right?
Yeah.
So the wave function we'll never see.
Yeah, we'll never
see it in real life.
Yeah.
When we measure it, we only see the particle one place.
Yeah.
But if we measure it continuously over and over and over and over and over again, we should reproduce the wave function pattern. It should look exactly the same.
Yeah.
So we should be able to see that probability distribution with enough measurements.
Yeah.
That's the real cool thing about probability, is that you actually can get your answer. You just have to repeat it multiple times.
Yeah, I say quantum mechanics is probabilistically deterministic.
That's pretty good.
It's like you have a defined set of range of
right.
values, but you will only get these values.
Right.
That's for sure.
Right.
You're not going to get
like with the infinite square well potential, you know that nothing's going to live outside of it.
So you have some kind of understanding of where the particle can be, at least.
Yeah.
But you just don't quite know exactly where at that instant the particles will be.
You do know what the probability distribution is, though.
Yeah.
It's pretty cool.
Yeah. Well, so now that you have a quick quantum mechanic primer.
Yeah, we've probably talked too much. We lost half the audience probably already.
No. This is for people who don't know what the hell qubits are. So maybe this.
But usually in YouTube it works better if you front load the topic first, and then you start trailing off.
Well, you explain
what
qubits are. I think that's a good.
Yeah, whatever.
But it was 26 minutes later.
Well, I mean, I kind of want to go. So now that if you didn't have a quantum primer, you do have one now, and so that'll be useful in kind of like explaining why we even use qubits to begin with. Like, because my question with this was what are some of the real life examples that we how do we create the qubits? You know what I mean?
Yeah, that would be really cool.
So,
which is something that lacks in pop science. Talk about quantum mechanics. Nobody talks about like the real. What the hell is a qubit in real life?
Yeah, how and why.
Right.
So I kind of want to answer the why first, because it's a lot of theory, and then the how is going to be illustrated by some of our videos here. But so why qubits? So care to?
We kind of already touched on it a little bit. It's because of that superposition / entanglement.
Right.
It allows us to have these to perform these different algorithms that a classical computer cannot, because a classical computer cannot be in superposition.
Yeah.
That you otherwise wouldn't be able to do. So you can do things like Shor's algorithm, which can show you which can figure out the factors of a really large prime number, right? Which has to do with RSA encryption. The modern encryption framework for banking and SSL certificates and things like that.
But I was going to say, most importantly, like what the differentiation here is that qubits are discrete as opposed to classical computing, which is like a continuous. Like sometimes you have a continuous flow. No, maybe that's disingenuous to say. Let's just say this. I'll just say this.
Yeah,
I'm gonna stick to my notes. So, rather than simply switching electron flow on or off, qubits require control over things like electron spin. So, to create a qubit, physicists have to find, or researchers have to find, a spot where they can access and control quantum number values. So things like, when we talk about spin, you can necessarily break down spin into like 4 quantum numbers, or no, maybe not necessarily spin, but
you can break down particles maybe into 4 quantum numbers, and sometimes more depending on what you're doing.
Right. The quantum numbers. Well, there's a principal quantum number n.
Yeah.
And
this is the classic chemistry stuff. If you've taken like general chem in college, you should know this.
Yeah, and but I think more importantly, with controlling spin, you have the azimuthal spin, quantum number L. And then
which we like to think of as orbital angular momentum.
Yeah, and then there's the magnetic quantum number spin.
Right, which we like to think of as the intrinsic moment of the electron.
Right.
If you imagine the solar system, Earth spinning around the sun would be the L azimuthal, and then the Earth spinning around its own axis would be the M, the magnetic quantum spin.
Yeah, and then there's...
Although nothing's spinning, so...
So don't get the wrong...
That's where physics and quantum gets you fucked up.
Don't get it
Nothing
twisted.
is actually spinning.
Yeah, don't get it twisted. And then last, the more famous one and the favorite one that everyone likes to talk about colloquially is the spin quantum number S. I think that's the one...
oh, wait.
Or is it L? L is the one that people refer to typically, or is it S?
I don't know.
Because it's azimuthal.
Did I mess up something?
No. You're right about the
You
azimuthal.
sure?
And then there's
What
the
about M?
magnetic, and then which is M. And then
spin.
there's this S, spin.
See, that always messed me up, the M and the S, because it's like M and S are anti-parallel or something, right?
Right, yeah.
But I don't really... Oh, because I guess M must be the actual intrinsic moment, and then S must be that actual angular momentum part.
Right, yeah.
Okay, so I should correct that. That's something that actually I learned only recently in graduate school because I was so confused by it. The angular momentum part and the spin magnetic moment part are different. It's just that we can write spin and angular momentum sometimes in terms of each other.
Yeah, it's SLM, I think, is what the SLM
yeah.
numbers,
But you have a separate spin moment, and then you have a separate angular momentum moment, the intrinsic angular momentum moment. And I think Mithana Yoga Nathan has a good video on spin about this and why you actually need the angular momentum part, because the whole Stern-Galak thing, you see this this is how they found out the dual nature of spin up and spin down. But then you ask yourself, like, why does it need angular momentum? Like, who gives a crap?
Yeah.
But that has to do with S.
Yeah.
It wouldn't produce the same effect if it didn't have angular momentum. So watch Mithana's video if you want to understand that at an intuitive level.
Yeah, and I mean, these basically are all components of spin angular momentum. Like the SLM and or whatever, I don't know what order, whatever order you want to put them in. They're part of a
L is orbital angular momentum.
Yeah.
So you said spin angular momentum.
Sorry, yeah, I meant to say like
angular momentum in general. You can say maybe
the quantum angular momentum in general.
But then M is not momentum either, so it's bad to even say.
I know
that.
this is the language. The language is awful, but I meant
just say quantum numbers.
I'm just saying. Okay, let me. This is why. Yeah, quantum numbers.
Yeah.
And they all have to. They're all relegated to angular momentum of the quantum system, like, because when we talk about Clebsch-Gordon, right? The Clebsch-Gordon coefficient stuff. When we're talking about angular momentum or total angular momentum of a like an electron per se. We're using these values, SLM. We're using the prepared state of a quantum system typically. And they do this.
Oh, I see. Because you can find J, the total angular momentum, if you know S, L, and M.
Yeah.
Okay.
Yeah.
Okay.
And so they do this or they use all this information in sort of quantum computing, because your prepared system, or you prepare your system in a way to where these numbers, these values, the total angular momentum. It has to be done very precise and very fine-tuned.
Yeah.
And yeah, it's fascinating how they do this, because
and the Clebsch-Gordon, I want to comment on that real quick, because you were talking about the Clebsch-Gordon table. I remember that bullshit from quantum mechanics. I was like, why the hell would I ever want to use this?
Yeah.
I hated it because it's just looking up a chart and figuring out numbers. But the reason it's important, I think, I've never used it, but I'm pretty damn sure that it's very commonly used in actual research.
Yes.
So you are computing Clebsch-Gordon numbers and things. Because you see people carrying around Clebsch-Gordon tables with them. So I'm pretty damn sure it's useful, especially in like nuclear physics, maybe in particle too, I'm not sure. But
definitely in quantum. I sent you there was an interview question.
Oh, you did, yeah.
That had this. You needed to know.
You
how
sent
to
it
use
on the
Clebsch,
Discord channel, I think.
You needed to know how to use the Clebsch-Gordon coefficient.
Oh, so that's showing you because they want to know if you know how to use it.
Yeah.
I surely would have to like go over that again, because I put that in my memory. But
yeah,
if you guys want to, that's a practical tool of quantum mechanics. If you're trying to get into nuclear research, definitely look up the Clebsch-Gordon table. It's CLEBSCH, I think, and then Gordon. That's going to be very useful, I think, in real life experimental physics.
And that's a good way to ascertain. I think the real intuitive picture to draw from the Clebsch-Gordon stuff is like how to calculate the math stuff.
Yeah.
And application, but the intuitive picture is more of the quantum chemistry bridge.
Yeah.
To get to those how you even ascertain these quantum numbers.
Yeah, it was cool actually taking quantum at the same time and trying to bridge that gap with my general chemistry knowledge, because I was like, I always knew these stupid numbers like PLS and or these PLSDM and shit,
or whatever,
DF and whatever. And you're like, why the hell do I need to remember this? Chemistry just feels like a bunch of arbitrarity. You're just memorizing all this crap for no reason. But then you start to connect the dots and, I see why this stuff is actually going on. When you finally in quantum mechanics, when you actually derive, the wave function for a hydrogen atom, you see how all this stuff actually comes about, and you get those spherical harmonics, with the YLMs, and then you see actually where all this stuff comes into play. you're like, oh, okay, it all makes sense now.
It's a beautiful picture once it's like.
And wasn't
shown to you.
Wigner-Eckhart theorem related to this as well? Or am I tripping out?
Yeah, I think that's how to discern which states are allowed and which aren't.
Okay.
Which configuration of states are allowed. So
But
that's another
asterisk
level.
on that because I don't
Yeah.
even remember what I'm saying there.
Wigner-Eckhart. Yeah, the Wigner-Eckhart theorem is like its own beast, but
That was another one of those things where I was like, why the hell am I learning this?
yeah, that's another tier of like having to know. But again, I think a lot of nuclear people use it, and then if you're going to be in quantum mechanics, you need to know because you're preparing your states. You know, you're having to work with this, but
Okay.
anyway, so once the physicists access these quantum systems, they manipulate them using light or magnetic fields to create superposition, entanglement, and other things. Typically in a research environment, you've heard Terrence say, did you say Hadamard gates and all this other stuff?
Well, yeah, those are quantum gates.
Yeah.
Yeah.
So
That's the superposition gate, which is why it's so important.
So, but we translate these. We have these operations, like putting a quantum system in superposition, using a mathematical representation
Yeah.
of the Hadamard gate. But the
Right.
way they do this here is to influence the electron spin. Researchers apply microwaves and magnets, and the magnets and microwaves together allow scientists to control the qubits.
I'm guessing they shine the microwave on it to put it in some like
oscillatory.
right,
yeah.
but it's the frequency has to be tuned very specifically because they're trying to get it to where where it's almost has enough energy to either rise up an energy level or not.
Yeah.
So it's in a superposition between energy levels.
Exactly. Yeah.
Yeah. So yeah, I don't really. Which one is that? Which kind of quantum computer is that?
This one is well. They're saying in general, this is how they approach defect quantum qubit defect structures, like in the diamond.
Okay.
The diamond nitrogen
Vacancy thing.
Yeah, nitrogen vacancy, and with aluminum. What did I say? The other ones, aluminum and silicon.
Okay.
Ones, but yeah, this is how they typically manipulate those. I can't say that that's the same for the superconducting qubits, because superconducting qubits work off the principle of having metal. Where they use a different approach. They use metal. They use a metal material, insulator, and then another metal material in a sandwich, and they call them Josephson junctions.
Yes.
Yeah.
So I can explain that one a little bit.
Yeah, go for it.
So that's the one I researched the most because it's the common one. And it seems that, of course, everything in the quantum computer is basically superposition at the end of the day. So it's like, how are you going to put the particle in superposition? And what they do is, like, as you mentioned, Juan, is it's basically an LC circuit. So you guys, engineers, are going to be definitely familiar. You know, LC circuits, an inductor and a capacitor. And what they do is, except the weird thing is, the difference is the inductor part is actually the special part because it's the actual Josephson junction. So there's several different ways you can do it. There's like 3 different kinds of superconducting qubits you can do. The main one is the charge qubit, or it's called like a Cooper pair box or something.
Right.
And then there's like a phase one, and then there's another one. I forget what it is. But there's different ways to utilize superposition, right? It's just the different types of ways you do superposition. But essentially, what happens is with the LC circuit or the Josephson one, what they do is with the charge qubit, I guess, what they do is they allow these Cooper pairs to tunnel through a Josephson tunnel junction, and there's a superposition that you have where I guess this is an asterisk moment. Qualifier. I don't know exactly how they do it, but I guess I give it some kind of bias or something where they don't quite know if it's going to go over the junction. So what you're counting, though, is these Cooper pairs. So essentially, if it tunnels through, it's the number of Cooper pairs that tunnel through is the superposition. So you can say like 0 tunneling or Cooper pairs do
You allow
tunnel,
a couple pairs,
and that's the superposition state there. So you can measure that current, I guess, or maybe the voltage there,
Right, the voltage, yeah.
and you actually can get out whether it's in super. Or you can get out the measurement then. this is kind of irrelevant a little bit, but I guess I can just explain it. So the digital processing side would be like, we use digital signals, but then ultimately those digital signals get converted into analog. So it's like voltages and stuff are all analog signals, meaning they're continuous range. So although your voltage 10 and 9 may read out the same digital signal, it's like in analog world, 9 and 10 are different, right? 9 volts versus 10 volts. So then it gets changed to the analog layer, and then it actually gets changed to the quantum process layer, which that analog signal actually does the work to do the quantum process. So it's almost like you have a link between two computers, really, if you want to simplify it.
Exactly.
You're clicking on your classical computer, but then that classical computer sends instructions to your quantum computer.
Yeah.
That's really all it is. It's not much more difficult than that.
No, yeah, for sure. I thought this was a cool little diagram because I never really saw it as an abstract kind of picture of like, oh yeah, you do have to interface with your quantum computer.
But you don't actually. You could just have a straight up direct line to your quantum computer if you knew how to do it right. It would just be crazy because
I guess
then you're doing machine code, really, right?
Right. But I guess that's kind of the laser process, right?
What do you mean?
I mean the laser ion ones.
All of them will follow that infrastructure, I think.
Oh, okay.
As long as you have a regular computer hooked up to a quantum computer.
Yeah.
Right, because it's really just saying this is how you connect your classical computer to a quantum computer. Because your quantum computer doesn't actually have a UI or anything, right?
No.
Like your regular computer is still going to be viable.
Yeah.
It's that interface to just tell your quantum computer what to do.
So yeah, you'll more than likely, especially for the superconducting phase one, I think you'll be sending like electrical signals to the qubit system, so that you excite your electrons. Let's say you have 2 electrons that you trapped in your potential well.
Okay.
So this is kind of the picture that, at the end of the day, and the theoretical models that we built are all built on Hamiltonians of our systems. So
which are just the energy equation.
Right, but in physics we always try to approximate our toy models and our real life examples. So that's why a lot of these, like the superconducting qubits, are kind of like easier to work with, I think, because they're kind of analogs to particles in a box. Like they create a well. Right, so it's easy to we understand particle in a box.
We love particle in a box.
We understand it really well. Yeah, we understand it really well, so we know what to expect.
Right.
For the most part.
Yeah, really. Right. It's like really a lot of physics is just the easy shit that we know to do.
Yeah.
If it's easy and you can somehow make it into something, then that's what we're going with first. Right?
No, really, because we try to approximate the simplest potential that we can.
Yeah.
Like the more complicated your potential is, the harder it is to really solve the problem.
Right.
Or solve the system, really.
It's just giving your mind a lot to think about that probably is not going to have much of a return. Like you need to simplify your processes.
Yeah.
Maybe things will be, but it's always best to start as simply as possible and then build up in complexity whenever you need to. Always try to make things as simple as you can.
Yeah. So in theory, that's how you would build. An application too. This is how they build these qubit systems. They take a metal compound and an insulating compound and another metal compound and create basically a sandwich. So they do this typically with molecular beam epitaxy.
Oh, okay.
I knew a guy in a research group that I worked with, well, adjacent to, I should say, that did molecular beam epitaxy to create these thin films and create these superconducting qubits.
Yeah.
And they would often test them, and the thing
It
is,
sounds like a topological insulator.
I don't know. I'd have to ask. I haven't talked to him in a long
Maybe
time.
I'm just off. I don't know. That's probably wrong. Scratch that from the record.
but in essence, like they would perform these measurements. They would have to write the patterns on them, using e-beam lithography,
right,
etch contacts, and so you would have these nanoscale, like little tiny metal insulator. Metal sandwich, and you would put the contacts on top, and then what I mean by that is you tell your
wire
e-beam,
bonding and stuff.
You write a pattern on the little thing, and you basically create conducting leads onto there, and then put the leads on, and then now your hard part is making sure you don't fry the damn thing.
Right.
I was reading that too, and I was like, "Damn, I feel like me and you, Juan, we could actually make superconducting qubit.
We don't, but we don't have
systems.
access to helium, unfortunately.
Oh, you need the helium.
Like superconducting to get to those temperatures.
No, I'm saying if we were in the lab.
Oh yeah.
Like I think we have all the skills to make one, which I didn't realize.
Yeah, we do.
Because I was like, oh shit, we know e-beam and you know, putting on the different resist layers and all this stuff. I'm like, we could make that. I never realized though. I was like, damn, we should get into quantum computing.
Of course, if we had actual lab equipment, but we don't.
I'm just saying we have the skills to do it though.
We do have the skills to do it,
which is kind of cool. I never realized. I was like, damn, maybe I should start applying to jobs in quantum computing. I didn't realize it was that much of a translation of my skills. Yeah,
that's why I apply for these positions, for these like quantum computing positions. But that's, if you're an experimentalist, that's how you essentially create one. You go through the I call it a cradle to grave approach. In my CV, I have like that I do a cradle to grave approach to device fabrication, and that's like you take something like if you want to create a Josephson junction, you fabricate the material that you need or the compound that's going to serve as like either the insulating layer or the metal layer, whichever you want. And then you take it into the e-beam lithography system or the SEM, and then you write a pattern on it, and then like we were saying, you deposit gold contacts or some kind of contacts that are going to run the current through your junction there.
Right.
And the hard part is making sure you don't fry the thing, like I was saying, because static electricity can burn your device.
Right.
It's
just so sensitive that
exactly
those large bursts of static electricity will fire your whole thing.
And
they're so small too.
And I've ruined plenty of them doing.
Sure.
Just I wasn't aware.
I think I have as well.
But you have to ground yourself, otherwise you're just like gonna ruin your device, and
you're
not gonna get the data you want.
And you'll never notice it until you look at it on a microscope and you're like, why is this all black?
It's literally. I was like, is this supposed to be this dark?
Right.
Well, yeah, I mean, a lot of the time you don't even. It's literally nanoscale, like the patterns that you write, and then like the little device thing that you make. So anyway, the point is that this is how they're typically created in a lab, but theoretically the hard part, at least for me, was always interfacing with that device, because especially if you're doing for qubit stuff. I didn't particularly work with qubit stuff. I was just working.
We've never worked with anything that sensitive.
Yeah, I was working with. I was trying to work in making MOSFETs or FETs, field effect transistors,
which are basically the modern transistor, like used in everything nowadays. Yeah, essentially.
And but yeah, they have a very similar process in making these devices, but but yeah, the hard part, as you will see, is not necessarily how to make the qubit systems that will allow you to make qubits, because a lot of it, we know the theory pretty well. It's like you try to make a system that approximates a square well potential pretty nicely, so you can trap electrons at your own, how would you say, leisure pretty much. The hard part is interfacing with the system so that you actually don't destroy your whole device, because there's a lot of noise. What is it called?
And retaining the coherence.
Yeah, exactly. Okay.
Because the thing is, to even retain coherence, you have to have a supremely low temperature sample, right? And then they have that's why you always see the quantum computers have this crazy chandelier shit. All of that chandelier, like 99% of it, is just to keep the particle cold and,
or the device cold.
Yeah, in a coherent state. It's like the chip is actually this really tall, small part. So everything is about the cooling and just maintaining that state.
Yeah, and a bath of helium, liquid helium. And it's a huge, we call them dilution fridges.
Yeah.
But there are these huge things that look like chandeliers, and they have like, I mean, it's all to
rings and stuff on them, whatnot.
It's all to thermally isolate your system, and keep it in a
coherent state,
in a superposition state, and especially for superconductors. Like for superconductors, you form, especially the Cooper pair ones. Yeah, you need to transition into the superconducting state to even do any of that. So so it's a lot of work with a lot of these, but the different methodologies are all to attenuate to this. And the thing is, the biggest takeaway right now for a lot of physicists is extending coherence time and error correction.
Yep.
And
that's the goal for everyone, pretty much. Because once you get long enough coherence time, you can actually do real computations. And once you get enough error correction, you can do even more computations. So it's like those are the keys to everything.
Yeah. As what's his name? Who's the guy who's like they hate us, or DJ Khaled? What's his name?
I thought he used to be the best.
We the best, yeah. But
Yeah.
they want us to. I don't know. He's always got like the against me mentality.
Yeah,
like
yeah.
Everyone's against me. If he was born in the early 2000s, he would be emo for sure. We the best music is what else does he have?
I don't know. I just know you smart, you loyal.
You smart,
I appreciate you.
I appreciate you.
But that was just more of a one-off meme.
But I thought that he was just like.
Maybe he does. I just don't remember.
He has like
slogans.
imagined haters. You know what I'm saying?
Yeah.
I don't know.
He's always talking about the haters. I don't know. I don't follow DJ Khaled closely enough.
Yeah.
Fupus Calidius, as H3 would say.
He's a clown. He's a clown.
Gotta
for
love
sure.
him though.
He's a character.
He embraces the meme, so I respect him.
He does, but I forgot what I was gonna say. To his why I even brought it up.
Yeah, I forget.
Whatever,
now,
it's
too.
fine. Anyway, let's transition to the videos here because I feel like they serve as a good
They're
synopsis.
long, though, so I don't know how much.
I'll clip this.
Okay.
So we're actually going to be interjecting a couple clips here, loosely, just so you guys know. It's producing the show. I'm going to be interjecting videos by Anastasia Marchenkova and also by Sabine Hossenfelder.
Sabina.
Oh, Sabina.
German. Or maybe Austrian, something.
I don't know.
But either way, they both have great videos on quantum computing hardware, and they kind of just talk about a couple of the quantum computers, specifically like, Majorana fermion ones, photonic qubits, trapped ions, and superconducting qubits. Although in this podcast, we mostly talk about superconducting qubits.
That's the only one I studied.
Well, because there's so many, and you can go so deep into any.
Yeah.
Like each of them have their own school of scientific papers,
Right.
essentially. But superconducting qubits, I think, were the most popular ones, really.
Yeah.
Yeah. But yeah, so just be aware of that.
Some qubits are solid state, so we build them and we create them. However, they're also natural qubits. They're made from things in the world around us. There's qubits made out of atoms and ions, and one example is a nitrogen vacancy center in diamond. That just means that instead of having a carbon atom in the diamond lattice, it's actually replaced with a nitrogen and an empty space. And this gives us really interesting properties. Also, there's qubits that are man-made, like superconducting qubits. One hardware option for quantum systems is a superconducting qubit, which is a design based on a Cooper pair, which is just a pair of electrons or any other fermion, which is a particle with a half-integer spin, combined with a Josephson junction. Superconducting qubits are created using microfabrication, so the same technology that's used to create today's silicon devices. One of the reasons so many companies were using the superconducting qubit approach is because of its similarity to classical computing. The silicon fabrication that we use for today's chips can be adapted and used for these qubits, with just a little bit of retooling, of course, but that's a huge advantage to this technology. Superconducting qubits work by circulating electrical current through a loop of superconducting material, which is a metal where electrical resistance actually disappears at low temperatures. The direction of this current flow actually represents the two different quantum states. These are these synthetic, artificial atoms that we've created that can be used as qubits. So the super cool thing about this technology is that we can actually build these circuits to be configurable because they are man-made. That means we can adjust their energy level, spectra, to exactly the properties that we want to have for these qubits. There are also two different designs, the Transmon qubit and the Flux qubit. And this is all controlled using electromagnetic pulses. I think one of the best papers that you can read on this topic, if you want to learn more about this superconducting qubit technology, is called A Quantum Hardware Engineer's Guide to Superconducting Qubits, and I'll link that in the description below. So for these qubits, to maintain their quantumness and isolate them from environmental noise, we actually need to put them inside a super low temperature cryogenic environment. That's the steampunk chandelier thing that you see a lot in all the cool quantum papers. This is called a dilution refrigerator or a cryostat. And actually, that whole thing is really, most of it is the supporting material for the chip. The chip itself is the size of any computing chip. It's actually very small, but that's all the hardware that we need to actually support the operations of the chip. The actual chip itself actually looks very similar to the chips we have today because, again, they're using the same silicon fabrication processes. But that's really not the only way that quantum computers can look. For example, trapped ion systems look totally different. Trapped ions are another hardware implementation of quantum systems, and they're usually made out of ytterbium atoms. First, as part of the trapping process, an electron actually has to be removed from the atom itself. That means these ions are now positively charged. That charge on the ions actually allows us to trap them using an electrical field into a line of qubits. And then we can take a laser and actually individually address, control, and measure every qubit in the system. These ions are now levitating in this vacuum environment above a specialized chip. So they're called laser cooled because they're almost stationary. Temperature, remember, is atomic motion. So how does this actually work? Well, if you think about it, it's kind of like stopping an elephant with maybe 1,000,000 ping pong balls. The ping pong balls, or the photons, are super, super tiny, but eventually the momentum, if you shoot so many ping pong balls at the elephant, it will actually stop it. And that's the same thing that we're doing with these lasers and these atoms. The photons from the laser actually hit the atom, slowing it down. Once the ions are trapped, an array of individual lasers plus one global beam is used to control the quantum system. The interference between the two beams actually controls what state the qubit is in, and the quantum state is stored in the electronic structure of the atom. There's a few common ways that we can store the electronic states. One option is a hyperfine qubit, stored in two ground state hyperfine levels. And another option is a ground state and an excited state, and this is called an optical qubit. So these lasers take the place of wires in traditional circuits, which means they can be fully connected. So a really good article on trapped ion quantum computing hardware is on this Oxford website by Professor Andrew Steen. Yes, the same Professor Steen, like the quantum error correction Steen codes. Another approach is to use photons, or light particles, as photonic qubits. These computers use an optical circuit based on squeezed light or single photon light pulses, light beam splitters, and photon counters, and they work at room temperature. These quantum states of lights are also controlled by laser pulses. These photons go through beam splitters and phase shifters to perform computations, and then photon counters read out the results. So there's still a lot of different approaches within this space. So some companies are using a collective atomic excitation, or squeeze state, while others are still using the photons themselves, so the individual particles of light.
Okay.
So what did you think about?
I thought she had some really good insights on it. Yeah, she gave some really good understanding of just the different architectures there are of quantum computing, and just yeah.
Which one did you think was the most interesting?
Well, I guess because right now I'm just interested in the superconducting quantum computer qubits, so that's the one I'm more interested in right now. Also, I just think it's got a lot of cool stuff involved, like Josephson junctions and whatnot, and even flux quanta for some of them. Like, it's more interesting to me. Tunnel junctions, like those are all things that
It's
I'm
right
really
up your alley too.
yeah,
right?
it's like super up my alley. So that's kind of the more interesting one for me. But the one I probably know the least about, or it seems more tantalizing, I wish I knew more about, would be like the topological stuff.
The Majorana fermion stuff.
Yeah, Majorana, because I don't know anything about that really.
Yeah, me either, but I haven't heard the Mariana ones. I mean, you can correct us if we're wrong, but the Majorana fermion ones are difficult because the Majorana fermions, they were like hypothesized, and I don't know if like we understand them well enough.
Yeah. I think they're more on the theoretical bleeding edge, which I don't really know much about.
I mean,
So I don't know much about Majorana fermions in general.
yeah.
It's kind of more of a particle physicist thing that I don't
It's like
see
a
that
quasi,
often.
because it's like a quasi particle, right?
No, Majorana fermions are just they're particles where they are their own antiparticle, I believe.
Oh, interesting.
And
Yeah, that's kind of hard. That's kind of hard to. I mean, for Microsoft to go all in on that.
Yeah. Well, maybe they had just some researcher who was really familiar with that, and that was their field of study. So that was what they went with.
Dang. Well, photonic qubits are also an interesting one, but I the one that I found the most interesting is the trapped ion ones, because that's the one I knew least about, but that seems to have a lot of credence, or at least a lot of
that would probably be the one I would study next.
Yeah.
Because the universities use that one, so there's probably a lot of good literature on it. But I think that one probably would conceptually make a lot of sense. Whereas the one that's Majorana is like, I don't even know where to begin on that one.
Yeah. Maybe in the future. We're probably going to be able to talk about trapped ions. Deserve its own episode, really.
Yeah. All this stuff. Each one deserves its own episode.
Each one
really.
does deserve an episode. So this one kind of served as as a primer to all of the qubit systems. But but here we go. We're going to do another video. We're going to do a follow-up video with Sabine Hossenfelder, and see what she has to say about quantum computing.
Superconducting qubits. Superconducting qubits are by far the most widely used and most advanced type of qubits. They are basically small currents on a chip. The two states of the qubit can be physically realized either by the distribution of the charge or by the flux of the current. The big advantage of superconducting qubits is that they can be produced by the same techniques that the electronics industry has used for the past 5 decades. These qubits are basically microchips, except, here it comes, they have to be cooled to extremely low temperatures, about 10 to 20 millikelvin. One needs these low temperatures to make the circuits superconducting, otherwise you can't keep them in these neat 2-qubit states. Despite the low temperature, quantum effects in superconducting qubits disappear extremely quickly. This disappearance of quantum effects is measured in the decoherence time, which for the superconducting qubits is currently a few tenths of microseconds. Superconducting qubits are the technology which is used by Google and IBM, and also by a number of smaller companies. In 2019, Google was first to demonstrate quantum supremacy, which means they performed a task that a conventional computer could not have done in a reasonable amount of time. The processor they used for this had 53 qubits. I made a video about this topic specifically, so check this out for more. Google's supremacy claim was later debated by IBM. IBM argued that actually the calculation could have been performed within reasonable time on a conventional supercomputer, so Google's claim was somewhat premature. Maybe it was. Or maybe IBM was just annoyed that they weren't first. IBM's quantum computers also use superconducting qubits. Their biggest one currently has 65 qubits, and they recently put out a roadmap that projects 1,000 qubits by 2023. IBM's smaller quantum computers, the ones with 5 and 16 qubits, are free to access in the cloud. The biggest problem for superconducting qubits is the cooling. Beyond a few thousand or so, it'll become difficult to put all qubits into one cooling system, so that's where it'll become challenging. Photonic quantum computing. In photonic quantum computing, the qubits are properties related to photons. That may be the presence of a photon itself or the uncertainty in a particular state of the photon. This approach is pursued, for example, by the company Xanadu in Toronto. It is also the approach that was used a few months ago by a group of Chinese researchers, which demonstrated quantum supremacy for photonic quantum computing. The biggest advantage of using photons is that they can be operated at room temperature, and the quantum effects last much longer than for superconducting qubits, typically some milliseconds, but it can go up to some hours in ideal cases. This makes photonic quantum computers much cheaper and easier to handle. The big disadvantage is that the systems become really large really quickly because of the laser guides and optical components. For example, the photonic system of the Chinese group covers a whole tabletop, whereas superconducting circuits are just tiny chips. The company PsiQuantum, however, claims they have solved the problem, and they claim to have found an approach to photonic quantum computing that can be scaled up to 1,000,000 qubits. Exactly how they want to do that, no one knows, but that's definitely a development to have an eye on. Ion traps. In ion traps, the qubits are atoms that are missing some electrons and therefore have a net negative charge. You can then trap these ions in electromagnetic fields and use lasers to move them around and entangle them. Such ion traps are comparable in size to the qubit chips. They also need to be cooled, but not quite as much, only to temperatures of a few Kelvin. The biggest player in trapped ion quantum computing is Honeywell, but the startup IonQ uses the same approach. The advantages of trapped ion computing are longer coherence times than superconducting qubits, up to a few minutes, and the other advantage is that trapped ions can interact with more neighbors than superconducting qubits. But ion traps also have disadvantages. Notably, they are slower to react than superconducting qubits, and it's more difficult to put many traps onto a single chip. However, they've kept up with superconducting qubits well. Honeywell claims to have the best quantum computer in the world by quantum volume. What the heck is quantum volume? It's a metric originally introduced by IBM that combines many different factors like errors, crosstalk, and connectivity. Honeywell reports a quantum volume of 64, and according to their website, they too are moving to the cloud next year. IonQ's latest model contains 32 trapped ions sitting in a chain. They also have a roadmap, according to which they expect quantum supremacy by 2025, and they expect to be able to solve interesting problems by 2028. Before I tell you about D-Wave, I briefly want to thank our Tier 4 supporters on Patreon. Your donations are of great help to keep this channel going. And you too can help us. Go check out our Patreon page, the link is in the info below. Now, what about D-Wave? D-Wave is so far the only company that sells commercially available quantum computers, and they also use superconducting qubits. Their 2020 model has a stunning 5,600 qubits. However, the D-Wave computers can't be compared to the approaches pursued by Google and IBM, because D-Wave uses a completely different computation strategy. D-Wave computers can be used for solving certain optimization problems that are defined by the design of the machine, whereas the technology developed by Google and IBM is good to create a programmable computer that can be applied to all kinds of different problems. Both are interesting, but it's comparing apples and oranges. Topological quantum computing. Topological quantum computing is the wild card. There isn't currently any workable machine that uses this technique, but the idea is great. In topological quantum computers, information would be stored in conserved properties of quasi-particles that are collective motions of particles. The great thing about this is that this information would be very robust to decoherence. According to Microsoft, the upside is enormous and there's practically no downside. In 2018, the director of quantum computing business development told the BBC Microsoft would have a commercially relevant quantum computer within 5 years. However, Microsoft had a big setback in February when they had to retract a paper that demonstrated the existence of quasi-particles they hoped to use. So much about no downside. The far field. These were the biggest players, but there are two newcomers that are worth having an eye on. The first is semiconducting qubits. They are very similar to the superconducting qubits, but here the qubits are either the spin or charge of single electrons. The advantage is that the temperature doesn't need to be quite as low. Instead of 10 millikelvin, one only has to reach a few Kelvin. This approach is presently pursued by researchers at TU Delft in the Netherlands, supported by Intel. The second are nitrogen vacancy systems, where the qubits are places in the structure of a carbon crystal where a carbon atom is replaced with nitrogen. The great advantage of those is that they're both small and can be operated at room temperatures. This approach is pursued by the Hansen Lab at QTech, some people at MIT, and a startup in Australia called Quantum Brilliance. So far, there hasn't been any demonstration of quantum computation for these two approaches, but they could become very promising. So that's the status of quantum computing in early 2021.
Yeah,
Pretty thorough.
pretty thorough. It seems to me like the far field ones are more like what we were talking about earlier, the defects in the solid state materials. So so yeah, that's kind of interesting. The one that intrigues me the most is the topological one. Now I'm kind of like, what does Microsoft see that no one else is seeing?
Yeah, I know. I don't know. It's just a new framework, I guess.
Yeah, and that's a topic that we're going to talk about. Well, it's slated. It's on the schedule.
Yeah.
The like what the hell people mean like when they say topology.
Oh, right.
Especially in the context of condensed matter.
Yeah.
And that's something that we have to dig in. And it might be a good way to kind of jump into something like a topological quantum computer.
Right.
What that would even mean or what that would even look like. So, so yeah. But yeah, I mean, I didn't know. This is kind of a great introduction to like qubits and like all the different types of qubit systems. So, yeah, that's cool. I didn't know.
Yeah.
I didn't know there was this many.
Well, there's just mostly these two. That's why I picked them.
Oh,
I'm sorry. You meant many qubits. I thought you meant the videos.
No, I meant the qubit systems.
yeah.
Like I didn't know there were that many, and I didn't know they were that far-reaching.
Yeah, there's a bunch. And even when I was doing, when I first came into our school, I was doing research, quote unquote. Not really. I was like
What?
What do you call it?
the lab grunt.
Gotcha. Yeah.
Doing research on quantum computing. It was in the context of
What would you call it?
like it was like microwaves related to.
Oh, I know what you're talking about. You're talking about like molecular. Were you talking about molecular qubit systems?
Yeah, it's molecular qubits, but it was it's like molecular qubits where you were shining it with microwaves and hitting some kind of resonance.
Yeah.
And then that resonance would, I guess, produce some type of superposition. I think with the
within the molecule.
Yeah, I guess within the cumulative spin or something of the molecule.
Right.
This is a heavy asterisk moment again.
Yeah.
I
think
don't
you were
really
there for a
remember.
short. You were kind of there for a short time, right?
Very short, and I really didn't care that much
Because I wasn't going to be with that group anyway. It was just when I was first transitioning into the school. And they were trying to figure out the relaxation times. And the relaxation times, I remember they were labeled like T1, T2. It's the standard relaxation time thing. So if you look up T1, T2, T3 in the context of
coherence times? Or?
Coherence times, I think you'll be able to find out what that means if you want more detail. But that's all I can remember right now. It was kind of interesting, but I was like, it seems like another one of these.
Molecular systems are they seem kind of like novel and interesting, but they don't seem like they have the scope of something like a Josephson junction qubit system. Yeah.
Right. It felt like a novelty kind of deal to me. I was like, it's kind of like a side project,
Yeah. Well, I mean, nothing, no knock against people that do study molecular systems. There
not
can
at all.
be, because the people that I knew that worked on that were super smart. I know which people you're talking about. It's a great group, but yeah, like very unorthodox.
They had a bunch of equipment and everything.
Yeah.
I was like, whoa.
Yeah.
But unfortunately, just didn't align with my interest.
Yeah. Yeah, I know the group that there was a group. I had the option to join a superconducting qubit group, but I felt like they were very limited.
Oh, okay.
In the instrumentation that they had access to, but I think, in retrospect, I think they probably were better off than the group that I ended up picking in terms of like applications to quantum stuff.
Oh, I see.
Yeah. Because
but you weren't really that interested in quantum applications at the time, were you?
I was, but I guess at the time I probably didn't know enough when I was picking labs to really like figure out like because I wanted to go into device fabrication because I knew that was going to the
Me
process.
and you had pretty much very similar choices for going into our labs.
Yeah, but mine, I just wanted to be able to, because I could the skills translate. The lab that I picked, the skills translated more than the one.
Like you're getting a job if you can fabricate. Well, I guess you don't know.
Well, because
in theory, you should get a job doing device fabrication.
Well, the thing is with the superconducting one, it's super niche. Device fabrication, like
there's only like a handful of groups, and then even if it's not a handful of groups, it's like a specialty project that they're only allocating a certain amount of people to.
Yeah.
Whereas device fabrication is just like we're always doing that.
Yeah. And that can translate to, you can even make Josephson junctions if you really wanted to. Yeah.
Right.
But yeah, super interesting. I would love to talk about the topological quantum computers next, if possible, just to kind of see what the hell's going on with that.
We'll see. We've been on a condensed matter tear though, so we might need to switch it up a little bit.
Branch out, yeah.
Or like do a little bit lighter physics topics or something. We'll see.
Yeah, we'll see.
But we've been inundating.
Oh yeah, fractional quantum Hall effect.
Yeah, we've been inundating people with condensed matter right now, and even our experimental one, episode 133, was about condensed matter research a lot. So maybe we should.
Maybe we should do something astro.
We should. We kind of neglect the shit out of astro.
Yeah, it's huge.
But that's just because it's so different, I feel like, from what we are normally used to.
Yeah.
Like, I don't know anything about planets or... I'm sure we can touch on some interesting things, though, if we really want to. Maybe like the James Webb or something. Because I think that's got to be coming soon, isn't it?
No
or maybe even Elon.
No clue.
Because Elon just had that launch with the first civilian astronauts.
Yeah, but it has to do with astrophysics?
I mean, it's space.
I just group everything in space with astrophysics.
Finding the escape velocity of Elon's rocket with a payload of whatever, 2,000 kilograms. It's probably not even. It's probably way more than that. Yeah, man. Yeah, I think we should do astrophysics probably next. But I would still love to keep talking about. Yeah, leave a comment. But I would still love to dive into. Actually, comment below on which qubit system you would like us to do a deep dive on. Out of all these that you just heard, which one seems the most interesting?
Deep dive scares me.
Yeah, yeah, I know, but that's the thing. It's better than. Yeah, I guess I like the deep dives more than I like the broad ones.
Yeah, me too.
It's
just the deep dives are hard because I have to study my ass off, and like now that I'm working so much, it's like harder to study.
Yeah, me too. I'm gonna be
apologies, guys, if the level of knowledge is a little bit lacking because I have not been able to study at the rigorous level that I'm usually able to do.
Yeah, but with that, folks, make sure you like, comment, share, subscribe. Follow us on our socials, right? You got them.
Socials are Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros.com is the website. Eigenbros 2 is TikTok. And if patrons, thank you guys. Thank you. So patreon.com/Eigenbros. Audio podcast every week, at least 30 minutes. And the Discord channel you will get access to if you join us on Patreon.
Yeah, come join us.
Yeah.
Yeah.
Talk some smack with me and Juan.
Yeah, all it takes is $1. And and we really
and actually some of these loophole finders are paying Canadian dollars and whatnot. So
oh, smart. Actually, I think the Canadians
so
Canadians more though.
Is it?
Yeah.
Oh. Well, then there you go.
Yeah, then it's even better.
Yeah, it's even better.
Just don't do Zimbabwe dollars. Okay?
Yeah, don't pay in. You can also pay in. Maybe we should have like a crypto setup.
Oh, a crypto setup. That's kind of
like a crypto wallets. Like pay in Doge, pay in Bitcoin.
Right. That would be cool, but we'll see in the future.
We'll see in the future. But anyway,
I gotta look at some things.
Anyway, folks, don't forget to comment below the questions we asked, and I think that's it.
That's it.
Yeah. All right. See you later, folks. Bye.